Hey guys, it is Tuesday, March 24th. I'm just going to kind of talk through the back half of that summary page, the one that I think was on the very front of what I sent home with you guys. A lot of this stuff is kind of review or maybe a little intuitive, but that doesn't mean it's not worth teaching. Let me just turn my lamp on. Usually makes that shadow a little less bad. There we go. So we have this idea of a conductor, things whose electrons are a little loose, and those electrons can flow easily. And so good examples of conductors are metals. So those valence electrons, the electrons in the outermost shell, are kind of really easily able to move from one atom to the next atom. Different materials like rubber and glass, that's not so. The electrons in that outer shell, they're in the outer shell, but they're stuck there. They don't really go from one atom to another atom, and so we call those the insulators. So they have rubber and glass. Wood is another good example. Air is a pretty good example. So anything whose electrons are kind of tight. Then we have the in-between, okay, semiconductors, where under certain conditions, or they can be made to behave, sometimes like insulators and sometimes like conductors. A lot of times, like it says, they hold their electrons, so they're insulators until they get a little bit of extra energy from something. So a really common example I like to talk about with semiconductors are like solar panels. Okay, so the solar panels, the ones that actually make electricity, so the boost, the energy boost comes from the sun. So the energy boost comes along, and all of a sudden those panels conduct electricity, and so they're able to produce that electricity from the energy of the boost and conduct it to, you know, the grid or whatever as the energy is added from the sun. We will talk a little bit about these ideas when we go through the concept development page in a little bit here, but we have different ways that things can accumulate charge. Okay, so there are three main ways. Okay, and they're not complicated if you don't make them that way. So we have friction, where you actually would rub something on something else and electrons jump from one thing to the other thing. If you did the PhET simulation I signed yesterday with the balloon and the sweater, that was charging by friction. Okay, so the balloon was rubbed on the sweater, the friction, brought those materials, sorry, my cat just jumped up, in close contact, and the sweater had a less tight hold on the electron than the balloon, so the electrons jumped from the sweater to the balloon. If you've ever, scooted across the carpet with your socks on, this is kind of the same process, right? And then if you get to something metal, you have accumulated charge, and so then when you touch the doorknob, that charge is released back to the doorknob, and that's you sparking your finger. And then we have charge by contact, and yes, friction is a kind of contact, but this is kind of a different thing. So if you think about, let's say you did that, you scooted across the carpet with your socks on, and you have accumulated negative charge. Okay, so you are now a negatively charged thing. If you touch a doorknob now, okay, so that spark is really electrons flowing from you to the doorknob. So now the doorknob that was neutral has now picked up electrons because it contacted you. Okay, so if it was neutral and picked up electrons, it's now negatively charged, right? So that's kind of charging by contact. So it's the contact with something that was already charged makes it charged, not the friction where it's a transfer from one thing to the other thing. Well, it is, but also wanted to mention, you guys, in your textbooks, this is not chapter 32, it's chapter 17. So if you are a person that really likes to read to get information, chapter 17 is your reference chapter. Again, not 32. This is from my old textbooks in Giltner. All right, so the third way something can accumulate charge is by induction. Okay, and so in induction, there's not really any direct contact. Okay, so again, if you did the simulation yesterday, when you had the balloon all charged up and you brought it near to the wall, okay, the electrons moved away from the balloon, and so the part of the wall close to the balloon became a little bit positive. And the side away from the wall became a little, or away from the balloon became a little bit negative. And so it became charged just because it was near something that was charged. Okay, it kind of became polarized. It had a positive end and a negative end. But imagine, if you will, okay, I have a neutrally charged metal bar here, and I'm going to bring a negatively charged bar close to it. So it's really negative. I'm going to put a bunch of negatives in here. Okay, so this bar has no charge, but it's still made of nuclei that are positive and have protons in them, and electrons that are a little bit more mobile. Okay, so electrons, remember, are negative, so it's got protons and electrons. And if this is really, really negative, the electrons can kind of move. Would the electrons want to move towards this bar or away from this bar? Well, we know like charges repel. So all these electrons, if they can, are going to kind of go to this side. Okay, protons can't really move, so they're going to be evenly distributed no matter what. Okay, but all these electrons kind of went to this side to get away from this negative. Okay, these aren't even touching, right? Because we know through Coulomb's law, those charges can interact across a distance. But now imagine if I broke this bar right now. Okay, if I broke that, my two halves would be this one side would be a positive, and this side would be negative. They never even touched this bar, but just from being close to it, charges were induced. Okay, so that's the charge by induction. And when we allow charges to move off a conductor by touching it, we say that we are grounding it. So a lot of times it's literally the ground. So you'll have, an end of an electric system that moves into the ground so that any excess charge buildup doesn't become dangerous. It can kind of release into the ground. But you could also say, again, back to the socks and the doorknob example, when you touch a doorknob and you feel a spark there, that is excess charge moving off of you onto a conductor that is the doorknob. So you're grounding yourself when you touch the doorknob. Okay, and last section here. Charge polarization can occur in insulators that are near a charged object, and this is very, very much like charging by induction. We just say that it has become polarized. And we're going to leave off right there for the notes. I would like to look at this page here. I'm not going to assign it to you. I'm just going to talk through a little bit of it. So these two are really easy. We're going to skip here. Says a rubber rod that has been rubbed with fur is negatively charged because rubber holds electrons better than fur does. So this is the rubber rod. It's just full of negative, right? It picked up those electrons earlier when it was rubbed against some fur. When the rod touches the metal sphere, some of the charge from the rod spreads onto the metal sphere because like charges repel. So all these electrons are all together. Remember, like charges repel. These electrons don't want to be close to each other. So when it touches this, some of them are going to hop onto the sphere, and when they get there, they're going to spread out and be as far away from each other as they can possibly be because like charges repel. So this is now negatively charged. Okay, so remember, we can charge by friction, contact, or induction. Okay, so how did this sphere become charged? Well, it became in contact with this that was already charged. So this would be charging by contact here. Same idea here. This time we have a positively charged rod that touches the sphere. Okay, so I want to emphasize protons are not going to move. Okay, the positive charge is not going to move. But what do you think is going to happen here? This is when I really wish I could interact with you guys a little bit more. But so we have protons and electrons in here. Some of the negatives are going to go onto the rod. Okay, so if negatives leave, what kind of charge is left over if negative exits to try to, they're pulled off of here because of this accumulation of positive charge. Well, if negatives leave, we're going to have some positive charge left behind. Okay, and again, the positives don't move. Electrons move, but if they leave, then we have positive left behind. So this would also be by contact, because these touched and the electrons moved directly from one substance to another. But again, for emphasis, this was neutral and now it's positive, but we didn't make positive charge, right? We just moved electrons. We were transferring charge, not creating it. Alright, so this says a positively charged balloon will stick to a wooden wall. It does this by polarizing molecules in the wooden wall to create an oppositely charged surface. So again, in this wall we have an equal number of positive protons and negative electrons. And the protons and the nuclei don't move, so I'm going to make them kind of even. And they said the balloon is overall positively charged. So those electrons in the wall that can move, okay, are they going to, if this is going to make an attractive force here, are those electrons going to kind of accumulate close to the edge of the wall, or are they going to move to be further away from the edge of the wall? Well, we know that it's attracting the balloon, and the balloon's positive, so those electrons must kind of have been pulled closer to the edge of the wall, so then we have this positive-negative attraction here. Alright. The backside here gets kind of wonky. I'm just going to leave it off. So your assignment is actually going to be this worksheet. We're going to do a couple of these, quote-unquote, together. But a few ideas on this first page to look at before we go. So this is just still that same equation that we've been using the other day. So it was force equals K times the product of the two charges times the, or divided by the distance squared. It's the same equation. But now we can actually plug in real numbers and figure out a real actual charge. So our unit of charge is the C, which is a coulomb. And yes, that's a really small number. That's an extremely negative number, or sorry, extremely small number, negative exponent. Okay, so remember, if I wrote this out, the charge of one electron, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's the charge of one electron. Okay, so instead of using that insanely small charge, okay, we use coulombs. Well, so 1 coulomb is the equivalent of 6.25 times 10 to the 18th electrons. So that's a lot of electrons, right? That's 625 with 16 zeros behind it, number of electrons. So it's a lot of electrons, but it's actually a size of charge that we can actually kind of work with. Okay. And then, remember in the last few videos I've said K. Oh, don't worry about K. We'll figure that out later. Well, here's K. K, when we're talking about air or a vacuum separating our charged bodies, is going to be 9 times 10 to the 9th newtons times meters squared divided by coulomb squared. And this is going to be one of those times where I feel like that unit is so cumbersome, you can just write out the number, and that's fine. And they put the K up here with the charges. Mathematically, it makes zero difference if you put it up there or you put it out front. Again, does not matter at all. But again, if we end up with a positive force, okay, that is repulsion, whereas a negative force is going to be that they are attracted. Alright, so I picked out 2 examples to do together, which only leaves you 3 to do by yourself. Alright, so I'm doing 3 here. It says, Inez uses hairspray on her hair each morning before going to school. The spray spreads out before reaching her hair, partly because of the electrostatic charge on the hairspray droplets. If 2 drops of hairspray repel each other with a force of 9 times 10 to the negative 9th newtons at a distance of 0.07 centimeters squared, what is the charge on each of the equally charged droplets of hairspray? Okay, so I'm going to just rewrite our equation here. Force equals K times our 2 charges divided by distance squared. So just like we've been doing all year, we got to think about units first. Okay, so force, as always, is going to be in newtons. So there's a number in newtons, so that's no problem. I can plug that in for force. 9 times 10 to the negative 9th newtons. K, I said, is going to be the same always all the time, so I look back and see what K was. 9 times 10 to the 9th, blah, 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 blah. Okay, and then we're going to put our 2 charges times each other on top. Okay, so something to think about on this one. It says they are equally charged, which means they're the exact same size. So I'm just going to plug that they're each x. So I could write x times x, but you know, when you take something times itself, a lot of times instead of saying like x times x, we're going to say x squared. Okay, and that's going to be a little bit easier when we get down the line here. Alright, so last thing we have is distance. They give us 0.07 centimeters. And right away when we see centimeters, we should have a red alert going off in our head that we have to fix that. Okay, so I have 0.070 centimeters. I kind of remember, what did Miss Faye say? How many centimeters are in a meter? Maybe I just remember. Remember there's 100 centimeters in 1 meter. So then my centimeters cancel out. I take 0.07 divided by 100, or I could think move the decimal 2 spots to the left. So I'm going to have 0.0007 meters squared. Alright, so there's a beautiful setup. Okay, so right now my unknown, my x squared, is times 9 times 10 to the 9th and divided by 0.0007 squared. So on the other side of my equation, I'm going to do the exact opposite. So I'm going to start with that 9 times 10 to the negative 9th. My unknown is times 9 times 10 to the 9th, so I'm going to divide by 9 times 10 to the 9th. My unknown is divided by 0.0007 squared. So I'm going to go times 0.0007 squared. Okay, and so if I do that in my calculator, that'll tell me what x squared is. So let's figure out what that is. I'm going to take the time and do it myself. Okay. Hopefully you all got a very, very shockingly small answer as well, which is I got 4.9 times 10 to the negative 25th. I'm just going to double check that. 9 times 10 to the negative 9th divided by 9 times 10 to the 9th times 0.0007 squared. Yep, okay. So that equals x squared. So when we see that our unknown is squared, we have to do the opposite of squaring something, which is to square root it. So I square root that answer, and I get 7 times 10 to the negative 13th. And what were these values up here? Remember, they were charges, and we have to think back, what was our unit of charge? That is the coulomb. 7 times 10 to the negative 13th coulombs. Okay. It does not say if they are positive or negative, and we can't really know, honestly. Because remember, anything squared would be positive. So if this was negative 7 times 10 to the negative 13th coulombs, we wouldn't know. Okay, we would have to be told if they were negative or positive. All right, let's do one more example here. It says Bonnie is dusting the house and raises a cloud of dust particles as she wipes across the table. If 4 times 10 to the negative 14th coulomb pieces of dust exert an electrostatic force of 2 times 10 to the negative 12 newtons on each other, how far apart are the dust particles at that time? Okay, so this time we don't know the distance. Okay, so we know the force in newtons, 2 times 10 to the negative 12 newtons. Remember, K is always going to be the same, which is 9 times 10 to the 9th. Okay, and then we've got our two equally charged things, and that's their charge, so that's going to go on the top. 4 times 10 to the negative 14th coulombs. I'm just going to write it twice. Okay, it's a little out of focus. There we go. All right, so I've got the charge of one times the charge of the other. They say they're exactly the same, so there you go. And then we have the distance between them squared that we don't know. All right, so this is one of those times where we have our unknown on the bottom all by itself. Remember the trick, when your unknown's on the bottom all by itself, it can trade places with the other side. So I'm going to rearrange to d squared equals 9 times 10 to the 9th. And then rewrite this. Negative 14 divided by 2 times 10 to the negative 12. Alright, so I'm going to have 9 times 10 to the 9th times 4 times 10 to the negative 14th times 4 times negative 14 times 10 to the negative 14th divided by 2 times 10 to the negative 12. So let's do that. Okay. So I got 0.0000072. Okay, am I done? Is that the distance between my two particles? I hope by now you're realizing, no, that's the distance between these two particles squared. So I remember I got to get rid of that squared, so I square root what I got, square root, and I get the distance between them to be 0.0027 if I round, and our unit of distance always the meter. Okay. So please answer 1, 2, and 5. If you get stuck, probably the fastest, most convenient way to contact me is Google Hangouts. I'd be happy to do a video chat with you to work through a problem, or we can just text chat. It's totally up to you, but I would like you to do those 3, take a picture, and if you could turn it in actually on the Google Classroom assignment, that works a lot better for me, because if you just email it, sometimes I get a lot of emails and I might see it when I'm not at my computer to grade it and forget about it. So if you could turn it into the Google Classroom, that would really be the best. But email would be fine too. All right. Thanks, guys. I'll hopefully see you tomorrow in a Zoom meeting at 11. That's Wednesday. All right. Bye.